Morning. Ladies and gentlemen, please take your seats so we can get started. The first session tomorrow is about EOS. It's a year in review. And for those of you who have been involved in EOS, you will know that there has been a lot of confusion over the past years. Everybody understood something different when they were referring to EOS. And in the past few years, also based on the work of the Industry Council, some clarity has, can you hear me? I hope so. So there has been some new clarity achieved. And you will now get the first-hand account of all the work that has been done from the absolute expert in the field, Reinhold Gaertner from Infineon Technologies. Reinhold.
Yeah, thank you, Guido, for the introduction. Good morning, everybody, and welcome in the early morning night show. For the European, I expected them to be here because of jet lag. They cannot sleep anyhow, but there are also a lot of Americans here, so thanks for coming. Yeah, my topic today is EOS. So some people say it's electrical overstress. Some people say it's end of story because once you title it EOS, there is no more communication. I want to talk a little bit about the difference between EOS or ESD. When you get now a device back from the field, there is always the question, was it EOS or was it ESD? And there was also the question, which pulse exactly did damage my device? And I want to talk a little bit about this. Then I want to report about the EOS work that the Industry Council has done, where we talked about key definitions. We talked about case studies with finding root causes. And then once this document was published, a group at USCAR picked up this work and applied it to their daily work, the EOS issues in the automotive industry. There has been discussed and now also already published a two-level process on support and information sharing, and I want to go into this. And then also what this group is doing next, which could be also very interesting for the rest of the industry outside the automotive industry. Yeah, and then I report about different activities outside the USA where this work has been picked up. So I was hoping that Terry is not in, but I've got this from his presentation. This is a typical chart that you can see. Probably everybody has such a chart, own company, which shows the failure rates. So here you see the root causes of the failure, and here you see how many failures you typically have. And you see the biggest column here is NTF, no trouble found, where the devices are sent back and nothing is really found on this. But then the second biggest one is EOS. So if you count all together, maybe about 30%, and where you have a real device ESD issue, that's a very small number. And if I would pick up a chart from our company, it would be the same. So EOS is really a much bigger problem than ESD, but in the past, in the industry, nobody really wanted to talk about it. Now, if you ask a couple of years ago, 10 different people, what is the difference between EOS and ESD? You got at least 12 different opinions. But the basic idea behind this was ESD, these are short voltage or current pulses injected from an external charged object into the device. And typically, the device was unpowered. And then it ended up in dielectric breakdown or minor thermal damages. Typically, we had a leakage current, increased power consumption, or functional fail. EOS, on the other side, this has to have been said, the big guys. It was a voltage or current pulses of different lengths it was injected via the application, and the application was typically running. So typically, the EOS damages happened in the past when the device was already powered. And then we had real massive thermal damages inside the device. And we had a short, a big leakage, sometimes even an open or a melted mode compound. Then a lot of companies started working on this topic, and this is a chart that I got from Christoph Dienel from Bosch. And you see what they did. They looked at the confirmed failures from 0 kilometers, so at the end of the car manufacturing line and out in the field, 2009 and 2010. And they tried to reproduce the damages in their lab. So they applied various pulses to the devices and checked whether it could be reproduced by EOS or ESD, differentiating between both in a similar way, so less energy than here. And you see 97% was due to EOS and only 3% really due to ESD, however you want to define it, but you see EOS is a much bigger problem. And you see here, that's what they actually did. They took the devices, opened it up when it comes back from the field. They seen a certain burn mark, and then they applied different pulses and tried to find exactly the same failure, same damage in the same location. And the conclusion they made is they can duplicate this only if they operate the device out of spec. So as long as they are in the spec, they cannot reproduce it. They also found that ESD was not a precondition, so there's no two-step process. Very often, we poor semiconductors get the information, yeah, I agree this looks like an EOS damage, but you already pre-damaged it in your fab. And typically, this is not the case because a lot of these damages happen at different locations if it's an EOS and an ESD event. And what they also found is, by looking at the root causes, most of the failures have been due to hot plugging or missing ground. Then the Industry Council picked up this work, and I think here I don't have to explain what the Industry Council is. These are all the members, and then they worked on a white paper for electrical overstress. The big topics have been understanding what EOS means in the field. So that's why we did a survey. Then we looked at the relation between absolute maximum ratings and electrical overstress. And we came up with a fishbone diagram where the various bones of the fish are typical root causes that are resulting in EOS-like damages. We collected case studies and used this as an opportunity to minimize the EOS returns. You can download this from the homepage of the Industry Council, ESDA homepage, and it's also published as a JEDEC document. Now, what are the important lessons that we got from the EOS survey? Though misapplication stands out as the most widely reported use case. So misapplication in the sense, I use my device, but not in the way it's intended to be used. And the root cause can really vary. Several root causes can result in the same damage, and sometimes the root cause is not truly electrical in nature. And one nice example for this is, for instance, that someone got a damage on his ECU, control unit for the car, and at the end they found out that from the connector, one pin was going into the wrong connector pin of the ECU, and by this, instead of applying small voltages, the supply voltage was applied to a signal pin, and then it resulted in a damage. So it was an electrical stress that damaged the device. But the root cause why the pin was bent was simply because the worker stepped on the connector, bent the pin, and by this, the issue happened. So sometimes the root cause might not be truly electrical. Also, it looks like or it is a big burn mark. If you talk to people, very often you find out that not many failures or damages exhibiting EOS-like signatures are completely resolved. As I said before, very often once the word EOS is out as a root cause, the communication stops and everybody tries to solve the issue on its own, and you have no lessons learned on this. To find the real root cause, you need a lot of information, but very often the complete information is not available or at least not forwarded to the companies that needs it. Therefore, developing a common information framework is very important, and we also found out that we need to define a link between EOS and the absolute maximum ratings. And we also found out that this is not only an automotive problem, it's an industry-wide problem, so everybody has EOS issues. So when we analyzed the whole things and discussed it, we found a couple of things. So previously, people used the terminology in a different way. So some called it EOS, EOS event, EOS damages, but there was no definition. We tried to find one. Of course, we found like 250 different, but none of them was really good one. And then the Industry Council defined that an EOS event is clearly defined as going over the absolute maximum ratings. As mentioned before, in the past, when it came to EOS, this was not so much an exchange of information and working together, but more finger pointing. EOS, that's the root cause is at the customer, at the PCB manufacturer or at the OEM. ESD root cause is at semiconductor manufacturer. And then the cooperation stopped. Now we want to have a clear communication and clear definition of terms. And also in the past, it was not clear who is responsible for what, but to really solve the issue, you need a closer cooperation between all parties involved. Now here is the definition for EOS as defined in the white paper of the Industry Council. An electrical device suffers electrical overstress when a maximum limit for either the voltage across the current through or the power dissipated in the device is exceeded and causes immediate damage or malfunction or latent damage resulting in an unpredictable reduction of its lifetime. So here now we have a clear definition, and EOS is now no longer end of story, but really electrical overstress. And then we come up with the definitions and the relation to absolute maximum ratings, and this is shown here. So on this graph we have on the x-axis the electrical stress, and electrical stress means everything. Also the normal signal that is going into the device, that's a stress for the device, and that's how we look at it. And here we have the probability of immediate damage. So we have 4 different regions. Let's go to region A4. Region A goes up to the maximum operating condition. So if your device sees only signals or stress that's within this area, then you have a safe handling in an application, and the device should not fail. If the device fails, although it has not seen any higher stress than maximum operating condition, then it's a weak device. It has been pre-damaged, something's wrong in the semiconductor manufacturing process, or so on, but it's not an electrical overstress. And then we have a region that goes beyond maximum operating conditions, but is still below absolute maximum ratings, and that's a region with restrictions. In this region, the device is still surviving. Typical things are, or the stress that you apply here, are all stresses that are defined in the data sheet. So for instance, in the automotive industry, the load dump, or all the ISO pulses, and also HPM, of course. HPM is definitely, or all ESD pulses, they are higher than the maximum operating conditions, but they are defined in the spec, and so if the device sees a stress here, it's not supposed to fail. But once you go over the absolute maximum ratings, you have a high risk for a damage. And we have this region C, where the device might survive, but when it goes back to region A, it's not guaranteed that it still has the same lifetime as it is promised by your supplier. And then if you go higher with the stress, it even gets damaged completely. So let me give you a short and simple example for this. If I have a device which has absolute maximum operating condition of 5 volts, so it sees only 5 volts, fine, nothing happens, it's in here. Then a bad operator forgets to wear his wrist strap. The device is specified according to 2000 volt HPM, and now the operator charges up and discharges at a voltage of 1500 volt. Now this is higher than the maximum operating condition, but it's still within spec, so below absolute maximum rating. So we are in this region here, and the device has to survive. So now, since the operator is now working faster and faster, and he's charging up higher, he's now charging up to, let's say, 2,500 volt. So this means he is now, and discharging, of course, into the device. That means he is now higher than the absolute maximum rating. This was 2 kV, and he is here. So the device might survive, but you cannot guarantee the lifetime. And then when the operator is charging up even higher, he goes maybe to 5 kV, he's in this region, and the device is damaged. So that means we have now a couple of ESD pulses that are applied to the device, and not all of them are resulting in an electrical overstress. Only if the ESD pulse is higher than the spec. Now that's why we should stop looking at root causes like ESD or EOS. EOS is the result, and ESD is the root cause. So they are not really different. ESD is just one of the root causes. Since we wanted to avoid that every failure signature that is a little bit bigger burn mark is immediately called EOS, we introduced a new terminology, which is called EIPD, electrically induced physical damage. And that means that's a damage to an integrated circuit due to electrical or thermal stress beyond the level which the materials could sustain. This would include melting of silicon, fusing of metal interconnects, thermal damage to package, fusing of bond wires or other damages because current or voltage have been too high. And this should now be used once you open up the device and have seen any burn mark, any failures, any damages, and not yet not yet call it an electrical overstress. We don't know the root cause yet at this stage. So then the Industry Council also come up with this nice graph, the world famous fishbone diagram. And we categorized the root causes that result in electrical overstress in 3 big categories. And we called it powered handling, switching AC operation, and unpowered handling. So in the unpowered handling, we have all the ESD events like an operator is charged up, a board is charged up, a device is charged up, and so on. But the device or the PCB is still not powered. Here in the powered handling, we have all the other issues where the device is already powered, and then we connect it. So like hot switching, hot plugging, and so on. And here we have the fast voltage transients. So, of course, if you want to convince people that they have to cooperate and to convince them that it's important to find the root cause, you need some examples, some case studies. And that's why in the white paper we already collected some case studies, and we tried to get a link to the fishbone diagram, and we described all in the same way. So we looked at failure occurrences, we looked at failure signatures, we looked at analysis and simulation, and also how we solved the issue. And this is an important first step. Of course, At the beginning, everybody said, oh no, that's IP, I cannot share, my customer will kill me. But it's not true. Within various organizations, we have already a lot of case studies, but of course we are looking for more. And I told my private bodyguard to lock the door in the back, and everybody has to give me a case study before he's leaving the room here. No food, no drinks, nothing, before you are not giving me a case study. One problem that we have, and that was a very important information that we could give to the end users, is that it's not really possible to do a failure analysis and then by looking at the picture, you know exactly what type of stress the device damaged. There is nothing inside the chip that collects the root cause, the number of stresses, the waveform, the date when it's happened, and the location. This is not yet implemented. If I would be a designer, I would have implemented, but I'm just a back tester, so I can't do it. And to give you an example, how it can be done or what it means is here. So this is a device that came back from the field, was opened up, top level, and we looked at this, and we have seen this nice failure. Of course, then someone had an idea what it could be, and we applied an HBM-like stress. TLP was used, and the stress was comparable to a HBM-like stress of 15,000 volt, resulting in a peak current of 10 amps. And with this, we got exactly the same failure. Same failure location and really comparable intensity of the damage. Now that's clear. Must be an HBM-like pulse, so one of the operators was charged up. Probably the operator is dead already. If he got a couple of 15,000 volt shocks, he might not have survived the 10 amps. But then the same device was stressed in a different way with a DC voltage and 3 volt above the breakdown voltage with a current of 300 milliamps, which is much, much lower than here. You see, this was maybe 10 volt range instead of 15,000 volt, and this was 10 amps, and here 300 milliamps, but for a much longer time. And, surprise, surprise, exactly the same failure mode. So the root cause could be something completely different. And therefore, it's so important to cooperate and to share a lot of information. Otherwise, we will not be able to find the real root cause just by looking at the failure signature. And when we had the first meeting at USCAR, some of the car manufacturers said, oh, that's an interesting information. We thought it's very easy for you just by looking at the failure picture to give me the root cause of the damage. So, and you can look up all the case studies in the white paper of the Industry Council. Then you also know how to write the case studies before you send it to me. And the outcome was the failure analysis only gives you a damage signature and does not tell you the root cause. As shown in this example, the failure signature and the damage can be duplicated by controlled experiments, but by different experiments. In general, EOS happens when the products are run outside spec. Misapplication, hot plugging, ground bounces, and so on. Everything outside the spec can damage your device. If you want to find a good solution to solve the EOS issue, you have to understand what could be the root cause, and you only can find this when you cooperate with all parties involved. We also looked at the factory and field return analysis to look at the possible root causes. So very often root cause is a poor grounding methods. And this can easily be mitigated by established guidelines. When we are trying to come up with EOS best practices, Terry is working with his working group on something like this. But very often a lot of things, at least in production, that are good for ESD are also good for EOS. like the grounding issue. If you want to learn something for the future, it's important to learn from field events. The problem is, if you, as mentioned before, a lot of these EOS cases are not analyzed in a very deep way. And if they are, the information is then locked in the manager's office and is not shared amongst others. Then it's difficult to avoid that something like this is going to happen in the future. Of course, automotive industry pose the most common risks. Everything is different there. And hot plugging is a persistent problem that could, for instance, be solved by having a longer ground pin, like USB has, for instance. Probably USB would not survive, especially the newer, faster ones, if they would not have the ground pin or the ground connection being longer than everything else to solve the issue. EOS by ESD, as mentioned before, is another cause, and this can be avoided by avoiding charging and discharging in the assembly lines if you are following the established guidelines. So the people in the Industry Council also put together some basic information that is needed for a good root cause analysis. So if you want to really find the root cause, you need a detailed description of all handling steps the part went through from the time it was received to the time the failure was detected. We come to this later on in a little bit more detail when we see how the automotive industry is doing it. You need a detailed description of the system and component failure symptoms. You should do something what the automotive industry causes A-B swap, so you take out the device, what you consider failed device, put in a new one and see whether it's working again. Because sometimes, although it looks like this device is damaged, but in reality it's just not running because another device is failing. You need the system data sheet, you need system schematics and board layout diagrams, you need the information for the powering up and system initialization. Although it's good to have a reference functional system so that you can really do some experiments on the system, and as much background information as possible should be shared. Though once the Industry Council has published the white paper, a group at USCAR, that's US, I forgot again, you have to help me. Okay, US Council for Automotive Research. You didn't hear the in-between that, I forgot it again. Though in this group, there was an initiative started to get some automotive strategy for EOS problem solution. And in the first round, the three different tier levels have been represented by 3 different companies. So here you can read who was involved there. So OEMs, tier 1s, and semiconductor manufacturer. And this was probably the first time that so many of them have been sitting in one room on one table. I don't think that it has happened before. This was started in September 2015. Some of the starting members you can find on this chart, the good-looking one here in the back, and also the best-looking one here, and also this one here. We sat together and started to work, and we come up with the results that we need 2 projects. One is a 2-level process for information sharing and support. After the discussion, we concluded that it is not possible that we solve or that we work on every damage, on every failure in the same way. You get hundreds of devices back, and if you want to analyze them in a very detailed way, do simulation and everything, that's not possible. Otherwise, every semiconductor manufacturer needs a 2,000 people FA group. And it's also that people on the other tier levels are involved. And then we also said there must be a systematic approach to give a guideline on how to solve the issues based on the target tree coming from, based on the fault tree, the fishbone diagram from the white paper. And the goal was really focus on the right things to be more efficient in the EOS root cause finding process. So if you have a really important thing, important case, not such a one-off, then work together on this, find the root cause, and let the information go to the other involved parties to avoid it in the future. So here you can see the table where we defined the 2-level support, or it's, as Jim is always saying, it's a 2.5-level support. So let's go through, look at this for a moment. So we have the level 1A. Level 1A is defined as single occurrences in a production within a 12-month period that have no evidence of a systemic signature, so the so-called one-offs. These are most of the EIPD cases that fall into this group, and the support we defined here is just a regular support from all parties where information has to be provided, which is defined in the Working Group 27 document from the ESD Association. And it's some information that's needed for working on this, but typically what's done then, the device is desoldered by the tier 1, sent to the semiconductor manufacturer. The semiconductor manufacturer confirms the failure with electrical measurements, maybe opens up the mold compound and looks whether there is a big burn mark or whatever, and then he can confirm an EIPD, and that's it. If more cases are coming like this, then we already have a lot of information. We'll show you this in a minute, and you can look it up in on the document, and then it's easier to work on the problem. Because here it does not make sense if I have a damage that happens only once to do a very deep analysis with simulation, trying to duplicate the failure and everything. This is a waste of time because you're not finding the root cause. Then we have the level 1B. These are still single occurrences, but now in more important applications, like safety-relevant applications, or product validation, design verification, and the safe launch period. Especially in these ones, you have less devices that are used, and if you have a failure there, it's more important. And here you have more extended support. And then we come to level 2. Level 2, these are really the important ones. These are repeat incidents. So we have a couple of failures, not only single occurrence, but a repeated way with a systemic signature. And then we need a more extensive support from all parties and a good cooperation. Otherwise, we will not find the real root cause. Yeah, I could have made it bigger. So, and how is the information sharing structured? And we have different blocks of information. So we have some general information, we have process data and look across, and this has to be provided by all 3 parties, OEM, Tier 1, and semiconductor manufacturer. So general information is of course important, like production data, process data, are there any abnormalities in your process? Sorry, and also look across. Look across means, for instance, this device is manufactured in millions and is sent to several customers. Do all customers have failures like this with the same signature? Then it might be a hint that something's wrong in the semiconductor manufacturing line. Or is it only happening in one application at one customer? Then it must have to do with the application of the customer and also maybe with the production side. And these things are important to find the real root cause. They are not available always at the moment. To reach a wider audience, we transferred the work from the USCAR to ESDA, and we have now a kind of joint working group between USCAR and ESDA, and we published already a document in June, I think, ANSI ESD SP27. This is a dual copyright document between ESD Association and USCAR, and can be downloaded from the homepage free of charge. The next step is then that we are working on an FTA document. That means we took the various branches and reviewed it by the different tiers and applied it to their processes. So you can easily read this here. It's a big Excel sheet that we filled out with various categories and subcategories. We already gave a rating here. What is the probability that we have a failure like this? And we explained the failure, gave some historical examples, and what to investigate in there. And then we put this together with a kind of rating here. And the bigger the line is, the higher the chances that something is going to happen. And if you have no idea where to look at, just start with this thicker lines. And like for instance here for the semiconductor manufacturer, powered handling at testing, that's a big issue where you should look the first time. Or here for the tier one, like charged people or inappropriate welding and these kind of things. The thicker the line, the higher the chance that something is going to happen. Or here at OEM, things like hot plugging are really dominant. So, as I mentioned before, we are working also here on case studies. We have the first one, and again, the door will be locked, and you are not allowed to leave before you didn't give me a case study, and it should be structured like this. What are other activities in the field? So in Germany, the VDA, which is comparable to USCAR and Verband der Automobilindustrie, we already started to work there, similar work like this. Again, OEM, Tier 1, and semiconductor manufacturer, and we want to apply the topic to the VDA framework. We had a workshop during the AEC meeting in April 2018 that Jim Roberts and myself organized, and I think it went very well. We had 80 to 100 people. We had a tutorial in Korea in March this year. They have not seen this before. We had one in Reno on Monday. We will have one in Dresden during the manufacturing symposium, and we are planning an online tutorial. And with this, I end my presentation. Thanks a lot.
Thanks a lot, Reinhold, for this excellent overview of all the developments and on the EOS area. Are there any questions? We still have a few minutes for questions. While you're thinking about your question, let me already ask one. You have shown that we have come a long way since the days of the finger pointing, and I think you pointed out that it is very important that semiconductor manufacturers and OEMs, tier ones, all work together in trying to figure out what happened in case of a failure. The Industry Council white paper made a big change in the approach, and I was just wondering, are you aware of the impact of this white paper? You showed the example of this USCAR initiative. Are there many other initiatives that also improve the situation?
Yeah, I mean, of course, the USCAR initiative is the first big one. It's really dominant, and some people already adopted this. Most of the companies waited for the publication of the document, which happened in summer this year. But a lot of companies are rolling it out at the moment in the automotive industry. In other parts of the industry, yes, they are interested, and they start working on something like this. For instance, the industry where the bank cards and ID cards are made, they also try to do something like this. And During our tutorial on Monday, we had half of the group was from automotive industry and the other half was from different parts of the industry. Of course, the questions might be a little bit different because if you use it for a cell phone and you ask for the mileage of the cell phone, it's maybe not the best question, but the general process can be used as well over there.
There's one question over there. Would you please state your name and affiliation?
Efraim Maroni, Tower Jazz. It's not a question, it's more a comment.
Even better.
Okay, so from my experience, we are a foundry, and few times we got customer complaints about failing in non-ESD related reliability tests, like op life and stuff like this. And many times it was the ESD clamp, because it is sometimes the only device suited between VDD to VSS. So it is more excessive to overstressing condition for acceleration, time life acceleration, stuff like this. And the customer call it ESD failure because it is the ESD device.
It's an ESD clamp, so
and I need to explain it that the product did not fail in ESD test.
Yeah. And you should call it an EOS clamp.
Yeah.
Make life easier. Thank you.
Any more questions?
Yeah.
Yes. Please state your affiliation.
Yeah, this is Nitesh from Intel Technology. So I had seen the slide with that region A, region B, region C. So is there any work going on by the working committee how to determine the limits for those? Yeah, so for example, for the pins, it is 3.355 volts. So how to determine the limits for those?
Yeah, I mean, the Industry Council wants to do more work on the AMRs. This will be discussed on Friday on how to apply this. In general, for these different regions, especially in the automotive industry, they do not have 4, they have maybe 3 regions, and they call this the region A and B, basically up to the absolute maximum rating, they call it spec. Everything that's defined in the spec, all the extra pulses that are well defined, this is spec, and as long as the stress is in the spec, this is not EOS. But there needs to be done more work to work in general on AMR.
Because if I look at region A, then it's just 10% of the nominal supply voltage.
Yeah.
But then what are the limits for region B and region C? So how to determine that for a device?
Yeah, I mean, as long as this, like for instance, in the computer business, a lot of people want to overclock the device to make the computer run faster. But once they are doing this without going back to the semiconductor manufacturer, this is an undefined situation. If the semiconductor manufacturer gives you a certain idea or an information, if you do a certain extra stress a couple of times, then this could affect your lifetime, going from 2.5 years to 1.5 years.
And exactly that is a question of what we should recommend to our customers.
Yeah.
How to determine how.
I mean, as long as the information is in the data sheet, he's not allowed to go over it. That's how it's defined at the moment.
Okay, thanks.
Okay, thanks a lot. Maybe one very quick question because we are running out of time.
Yeah, so I'm Stephen Hunter on Semiconductor. Just to alert everyone, there's a workshop tonight. Only 8 people have signed up. So as soon as you turn in your case study for him, go sign up for the workshop for what is AMR, absolute maximum rating. So please come to the workshop and express your opinions and give us some new data. We do have an active project that's going to start up in the Industry Council to try to determine if there's a method where we could all agree on how to determine AMR and how the customer should then interpret. But we need a lot of help to get this going. Thanks.
Okay, thank you. Let's thank the speaker once more.
Thank you.
We'll now take a short break. Please be sure to be back in about 5 minutes for the technical sessions, either in this hall or in the next one.